Okay. All right. So now what happens if instead of series, we connect it in parallel? Well, now if it's a parallel circuit, do this. You have current source, 8.3 amps. It's going from bottom to top, right? It gets here. It's going to make a right turn like this, comes up to this node, has no place else to go except come down. IB goes like this, IA comes like this. They again join up and form the 8.3 amps current source. But how many nodes do you see in the circuit? Two, right? Parallel circuit, there's only two nodes. If you see multiple nodes in a circuit, but they're all connected by wires, then they're the exact same node. So let's say if we say this is a node, this is a node, and this is a node. So we have three at the top, three at the bottom, just because of the way the schematic is drawn, but they're all connected by wires. As long as there's only wire between two nodes, they're the exact same node, right? Parallel circuit, only two nodes. So only two nodes, that means the same voltage Vs appears across the current source, appears across the resistors A and B. Okay. Important thing to keep in mind is that the voltage that appears across a parallel connection is a result of all of those resistors working together. And that's why it's the same voltage. It's the combined effect of all resistors working together. Okay. So you would have often read or heard the statement that in a parallel connection, voltage is always the same. Well, that same refers to the voltages for each one of those components. Okay. The reason it's the same is because all of those components are working together, and that's why they have the same voltage. Now, let's say if one of those resistors changes in value, is the voltage still the same? The actual numerical value for the voltage will change, but it'll be the same for all components. And that's the key distinction between in that statement. So when we say voltage remains the same, it means it's the same for all components. If any one of those components changes value, whether it's the source or whether it's the resistors, then the voltage will change. The numerical value of the voltage will change, but it'll still be the same for all components in that network. Okay, let's take a pause. Let me know if you have any questions. So I'm just making a note of what we just spoke or what I just spoke about. REQ or RT, as in Texas, stands for the total equivalent resistance as seen by the source. So In a series connection, Req is simply R1 plus R2 plus R3. Whatever resistors you have in series, you simply add them up. In a parallel connection, Req is the reciprocal of the sum of the reciprocals. Okay, so it's 1 over 1.14 plus 1 over 1.4. In the last couple of minutes, I just want to point out a couple of things about parallel networks. So in a series resistive network, let's say you're adding up 10 resistors. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, 8, 9, 10. What is the value of that Req? We need to calculate, but would it be greater than 10? Series connection, not parallel. Series connection, you have 10 resistors in series, you're getting 1 plus 2 plus 3 plus 4 all the way up to 10. Would it be greater than 10? Our brains do not have to think about it because we automatically know if you add something to something, logically it makes sense. Mathematically, you could have negative numbers and all of that. We're not talking about that. But if you're adding something, then always is larger. So the Req in a series connection is always greater than the largest resistor in that series network. Our brains don't have to think about it. For a parallel connection, doesn't matter what resistors you have, the total Req of a resistor network is always smaller than the smallest resistor in that network. So if you have a resistive network of 10 resistors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ohms, all of them are in parallel, and you find the total Req of this network, the answer must be less than 1 ohm. And we have to train our brains to think about that, note about it. The reason I'm pointing this out is because when you're performing quick calculations, sometimes there are errors. A quick verification check for a parallel network is that the answer must be smaller than the smallest resistor. If it's not, then there's some error in your calculations. Okay, that falls within the umbrella of what is known as a reasonable number. So when you're performing mathematical calculations, you're going fast and furious, and you need to know, do a quick verification check. If it's not smaller than 1, that means there's an error in the calculation, right? Okay, so we'll end class here today. We'll pick up here again on Wednesday, and then we'll also try and pick up the pace a little bit. Again, today's recording will be in 2 parts because Zoom kicked us out.